Hi, welcome to one and all. Next, we will be discussing about Dirichlet characters with the non-vanishing Gauss sums. In the previous section, we have studied about the separability of the Gauss sum. That is, the Gauss sum. If Gauss sum is separable, then we could see that if Gauss sum is separable, then we could see that absolute value of g of 1 chi whole square is k. Also, we have seen an important result that Gauss sum is g of n chi is equal to chi bar of n g of 1 chi. This is possible only when this GCD of n and k is GCD of n and k is 1. So here in continuation to that, what we are going to see is that this g of n chi is separable if nk GCD of nk is equal to 1, and the separability of g of n chi is equal to saying that g of n chi vanishes or equal to 0 for nk greater than 1. This we have seen in the last section. Now we are going to discuss further properties of this g of n chi equal to 0 whenever nk GCD of nk is greater than 1. This is what we are going to establish, the properties of this separability. So now our aim is to prove that when what happens when g of n chi is not equal to 0. That is, the theorem is like this: let chi be a Dirichlet character mod k, and assume that g of n chi is not equal to 0 for some n satisfying nk greater than GCD of nk is greater than 1. Then there is a divisor d of k, d less than k, such that chi of a equal to 1 whenever GCD of ak is 1 and a is equal to 1 mod d. So this is what we have to prove. So let me explain once more. We have to prove that if chi is a Dirichlet character mod k, we have to assume that g of n chi is not equal to 0 for some n satisfying n chi GCD of nk is greater than 1. That is, for nk greater than 1, this is not equal to 0. If this is the case, then we can find there exists a divisor d. We obtain a divisor d of k, where d is less than k, such that chi of a is 1 whenever GCD of ak is 1 and a is equivalent to 1 mod of d. So this is the basic assumption, and we have to prove that this is not equal to 0, or in the other way. So let us see the proof. For the given n, we are assuming that let q be the GCD of n and k. So clearly you should note that q will divide n and q will divide k. Now we take let d is equal to k by q. K by q is d equal to k by q means k is equal to dq. So clearly we can say d is k by q. Then clearly we can say that d divides k, because d is k by q. So d divides k. So since q is greater than 1, we have d is less than k. That is also true from here. So choose any a satisfying GCD of ak is equal to 1. This is what we are going to choose, a in this form. That is, GCD of ak is 1 and a is equivalent to 1 mod d. You take any example, like you take n is equal to 25 and k is equal to say 20, and you take then GCD of this n and k will be 5, and this d you can take d is k by q, so it will be 4. So d is 4, and now you take any number a is you can take 9 for example. Then clearly you can see that we have taken 9 because we have to make GCD of 20, and 9 should be 1. So that is true, and also that 9 is equivalent to 1 mod 4. So that condition is satisfied. So this way we have to take this number. So now we have to prove that chi of a is 1. This is what we have to prove. Now since GCD of ak is 1, as in the example GCD of ak is 1, in the sum defining g of n chi, we can replace the index of summation m by am. That is what we have done earlier also, because if ak is relative, a and k are relatively prime, that is gcd of ak is 1, then clearly the sum, if some m is a number which is running, m is the index of the summation, then clearly we can replace it by am, something like n, r and r in the previous theorem. So like that we can do this here also. So let us see what is the result coming up. G of n chi is equal to summation m mod k chi of m e raised to 2 pi I nm by k. This is the definition of the Gauss sum. Now this we can, m can be replaced by am, because this gcd of ak is 1. So sigma m mod k chi of am e raised to 2 pi I n am by k. Now this is multiplicative. Chi of am is chi a times chi m. So we can take this chi a outside, and summation m mod k chi m e raised to 2 pi I nm by k. Now we could see that now we have to obtain the value of this. What happens here? So for that, let us take a is constant to 1 mod d, that we have assumed earlier. We have assumed here a is constant to 1 mod d and d is k by q. Now we can clearly write a is constant to 1 mod d, means we can write a is equal to 1 plus some db, isn't it? Db, because a is constant to 1 mod d. So we can write a is equal to 1 plus db. And what is d? D is nothing but k by q. So we can replace that. So a is equal to 1 plus bk by q for some integer b. This is true. Now what we are going to do is we are multiplying the left side by nm by k. So a times nm by k is equal to this, here also nm by k plus bk nm by qk. So this is what done here. So here k and k cancel, you will get nm by k plus b nm by k by q. This is written as nm by k mod 1. This means that here you could see that this q divides n, isn't it? Here q is equal to gcd of n and k, so q should divide n also, and q should divide k. So here q should divide n. So q divides n means this part reduces to an integer. Clearly what we could see that is we can have this congruent to nm by k mod 1. So for more detailing, let me see this part. If you don't understand this concept, let us see this one again. Since we have written e raised to 2 pi I n am by k, this is what we are given here, e raised to 2 pi I n am by k. This is what given here. So here also the same thing, 2 pi I n am by k. Here also the same thing. There is a correction, a is missing here. 2 e raised to 2 pi I n am by k. This is what sitting over here. So we are taking this quantity. So here you could see that e raised to 2 pi I n am by k can be replaced by what we have done here. So n am by k can be replaced by n m by k plus b n m by q. So this is what I have done here. E raised to 2 pi I n am by k is replaced by this e raised to 2 pi I. Sorry, here it is not n am. This should be replaced by this one, nm by k plus bnm by q. This is what we have to replace. Anm by k can be replaced by 2 pi I nm by k plus bnm by q. Nm, here the a is not there, this a should be avoided. E raised to 2 pi I nm by k plus e raised to 2 pi bnm by q. This is what we have obtained from here. So we will replace this here. So e raised to 2 pi I n m, not a, e raised to 2 pi n m by k times e raised to 2 pi I n b n m by q. But this n divides q, so this part reduces to an integer. So this whole expression will become a 1. So that we are getting, what we are getting is e raised to 2 pi I n m by k. Please avoid this, I will correct it in the notes. This a is not there here. Here a is there, but here and here there is no a. So I will correct it in the notes. So here it is. We are getting is, so e raised to 2 pi I n m by k is same as e raised to 2 pi I n m by k. This is what is explained in this step. So now, so our sum, what we have done here is gn chi is chi a times sigma m mod k chi m e raised to 2 pi I n m by k. So this is this n am by k. Here it is n am by k. So this can be replaced by this e raised to 2 pi n m by k. So that is what we have done here. G n chi is chi chi g n chi is chi of a times sigma m mod k chi m times e raised to 2 pi I n m by k. What is this? This is nothing but g of n chi. This is g of n chi. So here g of n chi is same as chi of a times g of n chi. So this is only possible either g of n chi is 0. Otherwise this should be 1. That is the only case. So this, since this g of n chi is not equal to 0, it is already given in the theorem that g of n chi is not equal to 0. So clearly what we will get is chi of a is 1. So this is what the result is. So in that case, if we take this d and this a and a, there is a divisor d of k d less than k such that chi of a is 1 whenever a gcd of a k is 1 and a is constant to 1 mod k d, then clearly this chi of a should be 1. That is what we have to, if we are taking g of n chi is not equal to 0. So I hope you understood the result clearly. There is some corrections which I will do in the notes. So when you get the notes, you will get the corrected one and you can see that. Hope you have understood the theorem properly. Thank you for your patient listening.